Hi everybody, and welcome to your super fun snow day lecture. Considering the fact that we've already missed school on Monday because of less than savory conditions, and it seems like we've now traveled to the North Pole, we're going to do some lectures on videotape just to make sure we don't fall behind. That being said, if you have any questions, please be sure, shoot me an email, use the discussion board, or just stop by my office when the campus decides not to freeze. Okay, so we're going to pick up where we left off last time, in that we're forming carbon-nitrogen bonds. And so let's label this section of our notes, formation of carbon-nitrogen bonds. And where this fits in, remember, is we're learning different types of reactions we can do with substitution and elimination. One thing also, before I get too far into lecturing and forget about this, is that after about 10 minutes, you guys are going to hear a timer, and that's just letting me know that I need to switch to the next video. YouTube only has a 10-minute upload limit. Okay. So formation of CN bonds, and so what I want you to think in this case is that amines can also be used as nucleophiles. So using amines as nucleophiles. And so the way in which you can envision this working is taking some sort of electrophile which is pretty good at SN2. So for example, ethyl X, this works with both methyl and primary alkyl X groups. And you're going to use ammonia as a nucleophile. So ammonia, NH3, and we're going to use two equivalents. And we'll see why in just a second. Using a polar aprotic solvent to promote SN2 type chemistry. What we're able to do is we're able to alkylate, and so essentially put a carbon where originally there was a hydrogen on our ammonia group. So for example, we're going to wind up with NH2. So this is ethylamine. What we're also going to do is we're generating an extra equivalent of protons. So essentially we're generating acid in this reaction. So we'll need something to mop this up because our product in general is also fairly basic. And so the extra equivalent of NH3 that we've used is going to serve as a proton acceptor and generate an ammonium salt. So NH4X. Okay. So the mechanism of this sucker is relatively straightsforward in that what it's going to involve is it is going to involve the nitrogen using its lone pair of electrons to do backside attack on the carbon X bond, and remember X can be any sort of good leaving group that you'd imagine, chloride, bromide, iodide, tosylate, triflate, etc. And what this will give us is this will give us our protonated amine. As shown down here. Keep in mind, our product that we're looking for doesn't necessarily have this extra proton, so we're going to need to deprotonate that to form our final organic product. So a good way to do that is to actually think about this as instead of NH3, think about this as NH2 with an extra hydrogen here. What we then need to ask ourselves is, what is the most basic species in solution? Your inclination initially might be that, okay, I've got this really great X group that I've just kicked off here. Can this act as a base to pull off this extra hydrogen? The problem with this is that remember that good leaving groups are often weak bases, and so chances are this is not the weakest base in solution. To find our weakest base, we have to look up to our nitrogen species. It could be that our final product can use a lone pair of electrons to pull this off, generating an alkyl ammonium species, or we can use another equivalent of our ammonia. And this is actually just the purpose that we've added extra ammonia into this reaction. So what that will do is that will come, pull off the proton here, deprotonating it, and giving us our final product. Okay, so it turns out though that this type of chemistry is actually a really bad way of making amines. And so the reason for this is that these types of reactions tend to polyfunctionalize, poly meaning many. So let me just turn the camera. This truly is a one-man show. And so in our notes, let's write down polyfunctionalization makes this not a great way of making alkyl amines. Okay, and so what I mean by this is, let's take an example. Let's take ethyl bromide and say that we're going to react this with ammonia. We'll pick our favorite polar aprotic solvent of choice. I'll say DMSO in this case. And what you're going to get is you're going to get a mixture of different products that have added between 0 and 4 different alkyl groups to our amine. So for example, we've got the primary amine, so NH2, so ethylamine. We've also got diethylamine. Sort of looks like a bat, always fun. We've got triethylamine. Looks like a bat with a tongue. And then finally, we've got our tetraalkyl ammonium species, which is our IR. Okay? And throughout all of this, we're going to have extra equivalents of ammonia in here to pull off extra protons. And so there's going to be ammonium bromide, NH4Br. And so the distribution of these products is really going to wind up being related to how much ammonia we have to how much alkyl bromide. And in this case, what we've seen is there is actually 2 equivalents of our amine here relative to the alkyl bromide, which will only be 1. And so what we can see for the total recovery of, so a yield based upon our alkyl bromide as our limiting reagent shows primary alkylation occurring sort of in 57% yield, while our dialkylation winds up occurring in 24%. We have 3% trialkylation, and then we have a trace amount of our tetraalkylation. So whenever an organic chemist says trace, what that means is it is detectable, but not necessarily quantifiable. And so you can see, if you're trying to wind up getting either a dialkyl or a monoalkylamine, you can get detectable and isoluble product, but generally speaking, you're not going to have a whole lot to really write home about. And so because of this, chemists often turn to different mechanisms and different methods of creating alkylamines. And these are the kind of things that we're going to cover in later chapters. And they include, but are not limited to, things called Gabriel synthesis. You can also use an azide synthesis, or one of my favorites is you can use something called a reductive amination to create your alkylamine. And we'll talk about those in the upcoming future. So this is the first video of several for this lecture series. What we're going to move on to the second video is how we work with ethers and how we can use them as substrates for substitution. Stay tuned.